Welcome. So this is the first lecture for Math 442, which is Introduction to PDEs, or partial differential equations. And so what we'll be doing in this lecture is just looking at some simple examples of these equations, which are known as partial differential equations, and talk about some terminology that people typically use and that we'll be using frequently throughout the semester to talk about these equations, and then look at one particular type of example, which we can actually solve using a relatively direct method, which we'll see as the semester progresses. It turns out to actually be kind of unusual. And so to begin, I just want to briefly discuss, okay, well, what is a partial differential equation? And so as you can tell from the name, well, a partial differential equation is a differential equation as you're used to from maybe calculus 1 or 2, or from taking a class in ordinary differential equations, except the functions that are involved in this equation just are functions of more than one variable, right? So differential equation involving more than one variable. Right, and so for example, maybe you have a function that describes some kind of physical phenomenon, and maybe this phenomenon depends on, say, some spatial coordinates, right, where x and y are your spatial variables, right? Maybe it's a function on the plane, but maybe it's not just a function on the plane, but maybe it changes over time, right? So maybe you have a third variable to indicate your time. And so a differential equation will be some equation involving different derivatives with respect to these different variables, right? And maybe you don't just have two spatial variables, maybe you have three spatial variables, in which case your function would have four different parameters, right? X, Y, and maybe some Z to represent where it is in space, and then maybe a time variable to describe how it changes over time. And then the differential equation will involve different derivatives with respect to these different parameters, or excuse me, a partial differential equation. And so what's maybe a basic example that arises in the real world? So imagine so this is kind of a standard example, which we'll look at in more detail next week. So imagine a vibrating string, meaning maybe so look at the x-axis here. And so let's say, imagine that the x-axis is kind of like a string. And maybe let's say you sort of pluck a piece of the string up, right? So, right, maybe it's like a guitar string or a violin string or something like that, and you pull up a piece of the string as illustrated by the blue triangle I just drew here, and imagine that the rest of the string is just the x-axis. And so what we can do is define a function which I'll call u, and it's going to depend on the x coordinate, and it's also going to depend on t, right? So x is just the position on x-axis in the picture below, and t we're going to think of as time, right? So as t changes, you want to imagine time is moving forward, for example. And so what is this function going to be? Well, u of xt is going to be the displacement of the blue string here. Oh, sorry. At time t. Right, and so how do we measure displacement? Well, the displacement will be measured in terms of the distance from the x-axis, right? So for example, if this is this red little dot here is say x naught, what is the value of u going to be? Well, it's just going to be the height of the blue string relative to the x-axis, right? So the value u will take values on the vertical axis. And so this is going to be the value of u of x naught. And let's say we're at a fixed time. Let's say t is equal to 0 initially. And this is what the picture looks like when t is equal to 0, right? Just at the moment you're plucking up the guitar string. And so you can imagine that, right, as soon as you release this string and you let time start growing or let t start evolving, well, the string is going to move around, right? So this function u is going to change in time, and it's also going to look different depending depending which position you're at, right? Because if, let's say, instead of x naught, I have, like, say, x1 over here, well, right, the value of u is of course different over here, right? And so as time changes, you're going to get this complicated picture. And so it turns out that this motion can actually pretty surprisingly be described with a relatively simple partial differential equation that involves both time and derivatives in both time, in both the t variable and the x variable. And so it turns out, well, again, we'll go into this in more detail later. I just want to give you a glimpse. Well, it turns out that this function u obeys the following differential equation, which basically describes the motion in a simplified context of a plucked string like this, right? And so the equation is, well, if I take the second derivative with respect to time of u, that this is always equal to some constant c squared. The constant depends on like physical properties of the string and things like this, times the second derivative with respect to x of u, right? So if you have kind of a simplified string like this, and you pluck it at a certain point and then let the string sort of move up and down, evolve over time, well, this function u, which describes the displacement of the string, has to obey this equation. And so this is an example of a PDE, right? Because it's a differential equation, right? It's some relating certain derivatives of a function to other things involving the function. But moreover, it doesn't just involve derivatives of one variable, it involves derivatives of different variables that are related to one another, right? So these are the types of objects we're going to be studying for the whole semester, right? And so just as a bit of terminology so that you can connect this back when we return to this equation in more detail, this is typically known as the equation we just saw. This is known as the wave equation. Because it turns out that, right, if you think about a vibrating string, it's going to sort of move kind of like what you would expect a wave or a light wave to move. And so in simplified models, right, the reason we use the letter c here is because c is going to designate the speed of the wave, and c is typically used to designate the speed of light, et cetera. So we'll see more of this later in the semester. Right, okay, and so what's another example of another type of partial differential equation? And so this is typically called the transport equation. And we'll see more of this later today. And so let's imagine that I have, let's say, a pipe, which I'll try to draw here. Right, and let's say the pipe is going along the x-axis. And so imagine that you have some water flowing in the pipe. And so also imagine that there's a pollutant that's in the pipe. Right, so suppose some pollutant is placed, let's say, at the left end of the pipe. So let me use like kind of a red to denote the pollutant. And let's suppose that the water is moving, let's say, to the right, right? So let's say the water moves this way. Well, the pollutant is going to move along. The particles in the pollutant are going to be pulled along the pipe with the water, right? And so let me let define a new function. Let's say I fix a point x here along the x-axis, and let u denote the concentration of the pollutant above that point. Right, so u of xt is going to be the concentration of pollutant at time t and at position x. Right, so I have a function that I have some physical system which involves some particles spreading out along the pipe as the water moves. And so I can describe this physical system by defining a function which denotes the concentration at each point and at each moment in time. And so it turns out that once I define this function, you can show that it has to be a solution to another partial differential equation, right? And so it turns out that u will be a solution to the following equation, where if I take the partial derivative of u with respect to time, then this is always proportional to the partial derivative with respect to x, right? So there's some constant a such that if I, let me write it like this, if I take derivative of u with respect to t, this is always equal to some constant a times the derivative of u with respect to x, right? So a is some constant, right? And so this is another example similar to the wave equation of a partial differential equation, along with a kind of a simplified model of where it would actually show up in the real world. And so just a bit of maybe just some mention of terminology, since, right? So one thing you can see from these two examples is, well, the first equation, or the wave equation, is involving second partial derivatives, right? You're not just taking the first derivative, you're comparing the second order derivatives. And so this is an example of what's typically called a second order equation, because you have two derivatives in time and also two derivatives in x. And if we go down to the transport equation, this is typically called a first order equation, because it only involves first derivatives, right? Okay, and so what are some more examples of the types of equations we'll be studying all semester? So I'm not going to go into a whole like physical spiel about where these come from, but let me just give you some, just list out some more PDEs, or partial differential equations. Right, and so right, so one thing you can do is, let's say we return to the wave equation, and I look at, right, remember this equation was something like I take second derivative in t, and I right, sorry, I subtract off some constant multiple of the second derivatives in x. Just as a way of rewriting this, remember we saw that this had to be equal to 0, right? What I've done is just move the x derivatives over to the other side of the equation. Right, and so before we saw that this was 0, well, maybe in the real world, this is kind of a simplified model involving the string. Maybe if the wave system or the physical system is more complicated, there's going to be some other term here. One example which actually arises in practice is this is equal to, say, minus u cubed. And so adding on this other term, which notice, oh, sorry, I just made a mistake, realized I made a mistake here. Right, so adding on this other term, which notice also depends on u, kind of complicates the equation and makes it a lot harder to find solutions. And maybe the solutions, which are maybe harder to find, are more interesting physically, right? They arise in practice more often, right? So sometimes you'll have to modify these equations by adding an extra term like this, right? And so this is usually called like a wave with nonlinear, some kind of nonlinear interaction. And we'll talk more about what the word nonlinear means in this context in a few minutes. Some other examples, well, if you've taken a class in quantum mechanics or you've heard a little bit about quantum mechanics, so it turns out that if you look at a quantum particle, like maybe an atom or something like this, and you imagine like you want a function that describes how this particle moves, well, then this function necessarily obeys what's called the Schrodinger equation, which involves, well, you take the first derivative in time of your function, and this has to equal the complex number I, which is, remember, the square root of -1, times the second partial derivative with respect to x of the function, right? And so this describes the motion of quantum particle will obey this partial differential equation, at least along a line, right? So this is like a one-dimensional equation. Right, and so there are plenty of other examples of partial differential equations which arise in physics and math and engineering, et cetera, which if you look in the book, for example, there's like maybe 5 or 6 more different types of equations just listed out, just so you know that these things arise very, very frequently. So maybe it's worth taking a look at those to see some more quick examples. Right. Okay, and so, right, so what have we done so far? We've looked at spent a little bit of time discussing 2 main examples of PDEs. One was the second order equation, which is the wave equation, and one is a first order equation, which is the transport equation. So the main question you have in mind now is, okay, well, one, how did you actually find these equations, right? I'm just telling you that, okay, if you have the string, here's this equation involving second derivatives in t and second derivatives in x. How do you actually know that this equation accurately describes the vibrating string picture? And you can ask a similar question for the transport equation, right? Like, where does this PDE come from? And so we're going to answer those questions, not today, but starting in the second lecture. So that's one question you should probably have. And then another question you can have is, okay, assuming that this is a valid model for the physical phenomenon, can you actually find solutions, right? So how do you actually solve these equations? And so we'll also start discussing this equation in more detail, or sorry, this question in more detail over the next few lectures. And in particular, so if you look at the second example, or the transport equation, we'll see later today, time permitting, how to solve this equation. Okay, so these are sort of the big questions you should have whenever you see a PDE, right? The first is, why is this physically relevant? And then the second is, assuming it's relevant, how do you actually find the solution to the equation, right? Okay, but before we turn to these questions, I do want to first go over some notational conventions and some facts about terminology that people typically use for talking about partial differential equations. It's going to be, this part of the lecture is probably going to be a little bit dry because I'm just kind of introducing various notational conventions, but we should probably get it out of the way in the beginning because, right, I mean, whenever you learn a new subject in math, you have to inevitably learn sort of the new pieces of language that come along with it. So that's what we're gonna do now. Right, so we're just gonna talk about, again, before we return to more interesting examples, we'll talk about some basic terminology for talking about PDEs. Okay, and so one thing to point out initially, right, let me actually add a notation, right? One thing to point out is that typically, like if we go back to the examples we were looking at, right? So if I look at these equations, when I look at the derivatives, I'm using this partial derivative notation where I have like the d2 over dt squared and d squared over dx squared on the right-hand side. Typically, when you're writing these down, it gets kind of obnoxious to keep writing these partial derivative quotients in front of all your functions. And so there's a convenient shorthand, which the book uses and which most mathematicians will use. So shorthand for partial derivatives. And so you've probably seen this before in your multivariable calculus class. So for example, remember we had the wave equation, which was something like this. I take the second order derivative in time of my function u, which is really a function of x and t. And then I subtract off some number c squared times the second partial derivative in x of u of x. And this was all equal to 0, right? So this was our wave equation. Well, what's a convenient shorthand? Well, notice the first term, I just have 2 time derivatives. So what I'm going to do is just write u and then sub tt, right, to denote the first expression. And then I'm going to do the same for x, right? So this is going to be minus c squared uxx. And I'm going to say this is equal to 0. And so this means the same thing, right? So these subscripts are like kind of like a shorthand for writing partial derivatives. Right, and so this is I'll be using this notation frequently because it's a lot easier to write it like this than it is in the way that I've been doing it before. Right, and so for example, let's say I have my PDE, which is something like, let me just make up a PDE on the spot, maybe 3 times the second derivative with respect to x of u is equal to u times, like say, the derivative with respect to x of the derivative with respect to t of u. So I don't know what this PDE actually means, but it's an example of a partial differential equation. You can rewrite it as just, well, I have 2 derivatives in x, so I'm going to have u subscript xx, and then, well, I have the 3 in front of it, so, right, 3 times uxx. And then on the right-hand side, I have this function u, so I'll just leave that alone, and then I'm multiplying it by the x derivative of the t derivative. And so, right, so if I just looked at the derivative in time, maybe that's ut, and then you're taking the x derivative, so you would write utx, right? And so this is kind of a shorthand for the partial differential equation I wrote above, right? Another example of this notation. And so at this point, it's worth reminding you that if I have right, so this utx is an example of a mixed partial derivative, meaning it involves 2 different partial derivatives for 2 separate variables. And so remember that mixed partial derivatives are always equal, right? So if I take the derivative with respect to t and then with respect to x, that's the same thing as taking derivative with respect to x and then derivative with respect to t. And so this is true in general as long as the functions are like quote unquote nice enough. Right, and so what does it mean? Oh, sorry. Right, so what do I mean by nice enough? Well, the technical requirement is that all the second order derivatives are continuous. For our purposes, we don't really need to worry about this theorem, which is a theorem you probably saw in multivariable calculus, because we'll always be able to assume that all our functions are good enough that we can use this rule, right? So in this class, you're always going to be allowed to use the fact that you can switch the order of partial derivatives and they're always equal, right? So just worth reminding you here, right? And so I could have just as well written this as uxt instead of utx, and so there's no confusion, right? Because they're always equal if you mix up the partials. Okay, and so that's the shorthand for partial derivatives, which you'll see throughout the textbook. And so now I want to move on to another concept which may be new depending on your background in differential equations. And so this is, we're going to talk now about something called a differential operator. And again, these are really, I mean, it sounds fancy, but these are really just notational conventions, right? It's a way of talking about the equations that we'll be working with. Right, and so what is a differential operator? I'll abbreviate it DIFF. So a differential operator is a rule. You want to think of it as a rule, which I'll call, say, L. And what this rule is going to do is it's going to take a function as its input, and it's going to transform the function into another function. Right, so say it has transformed some function, say u, into another function, which I'll call, say, L of u. Right, and so you want to think of this operator, which we're calling L, as kind of like a function. Remember, a function has a domain, which are some points, and it transforms those points into other points, right? And so that's kind of like a rule that brings you from one place to another. And so this differential operator is exactly the same thing, except it's transforming functions into other functions rather than points into other points, right? But otherwise, it's the same thing as what you're used to calling a function. Right, and so well, we've already seen several examples of this phenomenon above, right? Because you can think of any partial differential equation as one of these operators, differential operators acting on something, right? For example, if we go back to the wave equation, you have your function u, and it's going to transform u into something involving, say, second derivatives with respect to t and second derivatives with respect to x, right? So for example, define L by, right, L of u is equal to second derivative of u with respect to t minus some number c squared times second derivative of u with respect to x, right? You have your input, which is the function u, and this operator L transforms u into this new function, right? So u is your input. And then whatever this combination of derivatives here is a new function, which we'll call LU, right? And so you can write the wave equation, and using this definition, the wave equation is just the equation, well, the right-hand side is L of u. And remember, in the wave equation, that all had to be equal to 0, right? And so this gives us a simplified way of talking about describing the wave equation kind of compactly. Right, and so typically, right, how do you write down what this operator is? Well, the first line I have here, define L by this formula, is a perfectly valid way of just defining what this operator or what this rule is. But typically, again, to maybe simplify matters, we would write this operator L involving as sort of what are the derivatives in what order and things like this, right? So in the wave equation I'm taking two derivatives with respect to t, and then I'm subtracting off c squared times second derivatives with respect to x, right? And so I kind of view LU as applying this quantity in brackets to the function, right? So LU is this stuff in brackets applied to u, and you're going to distribute this as if you would distribute multiplication, but when the derivatives hit the function, it doesn't mean multiply by the derivatives, it means take those derivatives, right? Right. And so just quickly, what's another example of such an operator? Right, so let's look at another example. Right, so I'm going to consider the partial differential equation where let's say 0 is equal to the first derivative with respect to x of u, and then plus some other function times another derivative of u, right? So here, let's say I put the function x times y times u of y, right? So this here is the function, say g of xy is equal to x times y. And so I'm in this differential equation, I'm multiplying the derivative with respect to y of u by this function, right? And so maybe more explicitly, what is this PDE? If I don't use the shorthand notation, this means that, again, u is a function of two variables, x and y. And so this partial differential equation is the equation 0 is equal to derivative with respect to x of u of xy plus whatever x times y is, right, times the derivative with respect to y of u of xy, right? Right, so this is what I mean, right? Again, so when I write down the x times y outside the derivative, it's this function, right? Okay, and so I can describe this using another type of differential operator. So in this case, well, what is my operator L? Well, LU transforms u to the function which is on the right-hand side of the equation, ux plus xy times uy, right? So I can think of this as like transforming my function. U becomes this new function. And so I can describe my PDE just by using the operator, right? So LU is equal to 0, right? Because if I go back to this equation, on the right-hand side, I have LU, and my equation says that that's all equal to 0. Okay, and so I want to point out that, well, in these two examples are of a special form where I have LU on the left-hand side and 0 on the right-hand side. They may not always be, they don't necessarily have to be of this type, right? For example, I guess this is example 3 now. Let me just modify the PDE from above. And instead, let's suppose that I have u squared is equal to ux plus xy times uy. Well, I can write this as, instead of as LU equals 0, I can write it as an equation LU is equal to u squared, right? Because on the right-hand side, I have LU, and then on the left-hand side, I have u squared, right? Right, so this notation is or this way of talking about differential equations is kind of flexible because you can use it in a variety of contexts to kind of simplify how you're talking about these relatively complicated objects, which are PDEs. And another thing, I mean, this is again maybe kind of a minor technical point. Maybe this is a little bit boring, especially if you've seen this before. But notice that there's more than one way to do this. Right, for example, instead of defining this operator L, for this equation, I could have instead, let's say I define L with a twiddle, L tilde or twiddle, whatever you want to call it. And let me define this as L twiddle U is equal to U squared minus UX minus UXY times UY. Sorry. Right. Well, if I consider the equation L twiddle U is equal to 0, well, that's just setting all this stuff up here next to the definition of L twiddle equal to 0. And so if I move the terms with negative signs over to the right-hand side, I get the same equation, right? And I'm just describing the same equation in different ways, right? So I'm using two different differential operators to describe the same equation. Right, so there's always some flexibility in doing this. I just wanted to point that out. right? There's not like a unique way to do this. So there's not like you must follow the rule and then that's exactly the way to do it. No, I mean, there's a few ways you can talk about PDEs in this way. Okay. Okay, and so it turns out that for our purposes, there's a very special class of these types of differential operators, which are called linear operators, which may be familiar from possibly a linear algebra class if you've taken it before. Right, so I just want to talk a little bit about linearity. Right, and let's suppose we have one of these operators L that we've talked about above. Right, so suppose L is a differential operator. So L is said to be linear if it satisfies two properties. So if the first property is, well, let's say I plug in a sum of two different functions, right? So I apply L to a sum of two functions, then this splits as the sum of LU plus LV for any two functions. Right, and so notice that this isn't just right for one choice of functions, it needs to apply for every single, no matter what function you pick, it needs to apply to those functions, at least as long as the derivatives are defined and things like this. So that's the first condition, and then the second condition, so this is kind of an addition property. The second condition has to do with multiplying by scalars. So if I have, or constants, so if I have, say, some constant C, and I multiply it by my function, say, U, then I can always factor out the constant. Right, so for any constant C and function U. And so of course, remember, constant just means that the C doesn't depend on whatever variables you're using for the function U. Right, and so if your differential operator has these two properties, we call it linear. And so the connection with linear algebra, if you remember, if you've talked about linear transformations before, this definition is really just saying that a linear differential operator is an example of a linear transformation, because these are the two properties you use to define linear transformations. And so what are some examples of linear operators we've already seen? Well, let me define L to be the wave operator, or the operator we saw for the wave equation, right, where I have second derivative in time minus c squared times second derivative in x, right? So this is linear. And so why is that? Let me just demonstrate. Well, how do you show this? Remember, well, I need to show that if I pick any two functions that I can prove both points 1 and 2 from the definition, right? So let's look at L of U plus V. Right, so what does this mean? This means take the second derivative with respect to t of u plus v, and then subtract off c squared times the second derivative with respect to x of u plus v. But remember, we have the addition rule for taking derivatives, and so whenever you take derivatives of a sum of two functions, it splits as the sum of the derivatives, right? So this first term, and this is also true for second order derivatives, et cetera. So this is the same thing as second derivative with respect to t of u plus second derivative with respect to t of v. And then similarly for the x term, this is the same thing as second derivative with respect to x of u plus second derivative with respect to x of v, right? And so since the derivatives split like this, everything will distribute, right? And you'll get the requirement, right? So let me write that out in detail just to do it maybe once, right? So then it follows that if I now expand everything, that I get L of, u plus v. L of u plus v is equal to, well, the first term I had d2 dt squared u plus d2 dt squared v. And then I had minus c squared times second derivative with respect to x of u plus second derivative with respect to x of v. And so now if I rearrange this and I gather all terms involving u and all terms involving v, you'll see that this is equal to, let me use the shorthand. Well, if I rearrange this, I get utt minus c squared uxx, and then I have plus vtt minus c squared vxx, right? And so this proves property 1, right? And then if you want to do property 2, well, you have to pick any constant c and show that that distributes in the way listed. And you can check that yourself. Maybe pause the video and just write it out quickly on a piece of paper. It's relatively easy to check for this example that property 2 is also true. So I'm going to skip that part. Right. Okay, and so that's an example of a linear operator. And so it always helps to not just see an example of something that satisfies the definition, but also a non-example or something for which the definition does not apply. So let's look at an example like that. Right, so let's define maybe my operator L of u. Let's say I look at, maybe I take the first derivative with respect to x, I add in the first derivative with respect to y, and then maybe I add in u squared, right? And so let's suppose I define this operator. So this is not linear, right? And so how do you actually show that it's not linear? Well, you just have to show that either bullet point 1 or bullet point 2 is not true. Right, and so there are a few ways to do this. So for example, let's check test against condition 2. Right, and so condition 2 is if I multiply u by any constant, then that constant should factor out of the equation, right? Right, so let's consider the function c times u of xy, where c is any constant. Right. Well, what happens if I apply my operator L to c times u? Well, that means I need to take the derivative with respect to x of cu, and then I need to take the derivative with respect to y of cu, right? Add those together, and then also I need to square my function, right? So I need cu squared, right? And so if I simplify this out, well, remember that if I multiply a function by a constant and then take a derivative, I can always factor out the constant, right? This has nothing to do with taking derivatives, or sorry, it doesn't affect the derivative because you can always factor out constants. And so similarly for the derivative with respect to y, I can factor out the c. But what do I have in the third term? I have a c squared times u squared, right? And so it's certainly true that I can factor out c here, right? If I factor out c from the expression, I get ux plus uy, but then I'm left over with this other term, c times u squared, right? And so in general, this is not equal to u squared in general. And so what this shows is that even though I could factor out c somehow, that this is not equal to c times L of u. Right, because the term in brackets is in general not equal to L of u, right? And so this shows that it's not linear, right? So L is not linear, right? And so you'll have a list of homework problems where you can get some more practice working with describing equations involving operators and checking when they're linear and when they're not linear and so on. So I think for everyone, this should hopefully not be too technically demanding. It's just sort of more of a matter of getting used to the notation and getting used to this way of talking about these equations. Right. Okay, and then one final bit of notation. I'm going to break this up into two parts, right? So suppose L is a differential operator. And suppose L is linear. So the equations of the form, right, let's say I have a linear operator L, and I have, say, LU is equal to 0, sort of like what we saw, for example, with the wave equation, if you go back in the lecture. So this is called a homogeneous linear equation. And so this notation or this terminology should hopefully be familiar from your class in differential equations. Homogeneous always means you have 0 on one side of the equation, and then you have some differential operator on the left side, and it's linear if the operator is linear, right? Oh, sorry, my bad English here. It should be R. Right. And then similarly, well, let's suppose I don't have 0 on the right-hand side. Let's say I have an equation of the form LU is equal to G, where G is some other function. So these are non-homogeneous linear equations, right? Right, so if in the book you see, or in the future you hear me saying a homogeneous equation, it just means 0 on one side and operator on the other side. And if you hear non-homogeneous, it means the operator is on one side and some other function is on the right-hand side. And linear means that it's a linear operator. Okay, and so why have we spent all this time going through this sort of technical terminology, trying to distinguish linear from nonlinear, et cetera? Or sort of more succinctly, why is it important to know whether or not an equation or a PDE is linear? Right, so there are actually a lot of answers to this question. Well, again, throughout the semester, it'll hopefully become a little bit clearer why it's worth immediately isolating this particular type of equation. I can at least give one answer to this question now, which is, right, let's suppose that you have U and V are both solutions to, for example, the equation LU is equal to 0, right? So for example, maybe you think of L as the wave equation, right? I have two different waves or two different functions that describe waves, two different functions which obey the wave equation that we saw at the beginning of the lecture, right? So this tells me that L of U is equal to 0 and L of V is equal to 0. Well, if my operator is linear, notice what happens if I apply L to the sum of the two functions, right? If these are completely arbitrary functions, all we know is that they're solutions to some particular partial differential equation. If the operator happens to be linear, well, that means I can split this as LU plus LV. But remember, both of these things are 0, right? Because we're assuming that U and V are both solutions. And so therefore, L of U plus V is also equal to 0 because 0 plus 0 is 0. And so U plus V is also a solution. And so this is only true in general for linear operators or for linear equations. And so this is a very important property of linear equations, typically called the superposition principle. Right, so if you think about it in terms of the wave equation, or if you think about it in terms of superposition of waves or adding different waves together, the fact that the wave equation is linear translates physically to the fact that if you have two different individual waves traveling at different frequencies and you combine them linearly, then that's also going to describe some kind of wave, right? So. Okay, and so that's finally, I think, about it in terms of the terminology, the new terminology to introduce. So soon we're actually going to be able to look at a specific example of a partial differential equation and start talking about how to solve it. I just want to say a little bit more before we do that about some more kind of background or introductory material. And so what I want to discuss again briefly is just the difference and I'll put this in quotes because maybe it's kind of vague, the difference in complexity between PDEs and the type of differential equations you're more used to working with probably, which are ordinary differential equations, or usually called ODEs. Right, and so remember, ordinary differential equations, or ODEs, these just involve one variable. Right, and so sort of the quick, easy answer, well, what is the difference between PDEs and ODEs is, remember, of course, PDEs involve more than one variable, right? And so it turns out that just the act of adding, say, one more variable or two more variables kind of like immensely complicates the investigation of these equations, right? So partial differential equations are much more challenging in general to understand than ordinary differential equations. Sort of like several magnitudes of order more difficult in some cases where you would think that they would be comparable. And so we can see this in a simple example that I think illustrates this phenomenon. So let's suppose that we have just a function of one variable, like say f of x. And so let's suppose that f is a solution of the following differential equation. So the second derivative of f is 0, right? So hopefully everyone knows how to solve this. Right, and how do we solve this? Well, I have two derivatives on the left and I have 0 on the right, so I can just take antiderivatives twice and I'll get kind of a general form of a solution, right? So, well, how do you solve this? If I take one antiderivative, then f prime has to equal some constant a. Right, so I know that, I don't know exactly what f prime is, but I know it's at least a constant function. And then if I take another antiderivative, well, that means that f has to be linear, right? Because if I take antiderivative of a, this says that f of x has to equal a times x, and then maybe plus some other constant b. Right, and so in particular, f has to describe a line, right? This is the equation of some line, and we already know like all the solutions. Okay, and so, right, notice that if you vary a and b, or you pick different numbers for a and b, you'll get different solutions, right? And so if you actually wanted to be more precise and say, well, what are the values of a and what are the values of b? Well, in general, of course, you can't answer that question, right? Remember, you have to prescribe some initial conditions. Which you can use to then give you more information, which may allow you to further specify what those constants are. Right, so for example, let's say you knew that f prime of 0 happened to be 1, and maybe f of 0 happened to be 2, right? These are some initial conditions. Well, then I can use this information to solve for a and b, right? Then the first equation would tell me that a has to equal 1. And then given that a is 1, you can use the second condition to determine that b is equal to 2. In fact, for this condition, you don't actually need that, but right. Right, and so, right, so this is a very simple ordinary differential equation. We specified two initial conditions, and you completely understand all solutions. Right. Okay, and so now what I want to do is look at the analog for, let's say, a function, say u of xy, which is a function of two variables. Right, and so let's suppose that u, the second derivative of u with respect to x, is equal to 0. So right, so it's a very similar form to the equation, the ordinary differential equation we were just looking at. We're just assuming now that the function has more than one variable, right? It's a function of more than one variable. Right, so how can we actually solve this? Well, once again, you can take take antiderivative with respect to x, you're still allowed to do that, of course. Right, and so you can take the antiderivative to eliminate one of the partial derivatives on the left-hand side. So on the left-hand side, I'll have just one derivative with respect to x. But now what happens if I take the antiderivative with respect to x of 0, right? Well, remember that this function is allowed to depend on another variable y also. And if I have, let's say I have some function g of y, which only depends on y. Well, if I take the x derivative of the right-hand side, that's going to give me 0, no matter how complicated the function g is. And if I take the x derivative on the left-hand side, that's going to give me uxx. And so if I take one antiderivative, instead of just having a constant on the right-hand side, I have an arbitrary function of y. Not just a constant, but it could be a general function of y. And so now if I take another antiderivative, what's going to happen? Well, on the left-hand side, I'm just going to get u, right? Because I'm inverting there, or getting rid of the derivative by taking an antiderivative with respect to x. Well, now on the left-hand side, I'm going to have to take antiderivative of some function of y, right? So what's the antiderivative with respect to x of g of y? Well, it's going to be some number, or it's going to be x times g of y. Right, so you have sort of a linear like term. It's linear in x, but there's this other complicated function in y that I'm multiplying by x. And then there could possibly be some other function, let's say h of y, that I'm adding on. Right, and you can check now that if I differentiate this equation with respect to x, right, well, the h of y, since this only depends on y, it's going to go away. It's going to become 0. And then this term, well, if I take derivative with respect to x of this term, I'm just going to get g of y. Right, so this is indeed the antiderivative, or an antiderivative of ux, right? And so in this situation, this is my general solution, right? And so g of y and h of y can be any functions of y, not just constants. Right, and so hopefully in this, right, this it wasn't too hard to find kind of like the general form of the solution for this particular PDE, but hopefully this illustrates that even in this very simple example, partial differential equations are much more complicated than ordinary differential equations, because here g and h could be constant functions, as we saw in the last example, but they can also be like anything you want, really, as long as they're differentiable, right? For example, maybe g is like e to the 7y squared, and h is like log of y squared or something like that, right? And that would be a perfectly valid solution. And so, right, and so remember in the last example we had these, or sorry, in the one variable example we had these particular constants that arose in our solution, and in order to determine what they were, we needed some kind of initial conditions. And so these initial conditions were the following, right? The first derivative is equal to 1, for example, and the second derivative at some point is equal to 2. If we try to do this for the PDE, right, for example, let's suppose that I know that u of 0 and y is equal to, right, so what did we do? We had 2 for the, let's say this is equal to 2. Well, then if I plug this into the previous equation, this tells me that, well, when I set x equals 0, well, I plug in 0 here, so the term involving g goes away, so I get h of y. And so this would tell me that h of y has to equal 2. But there's no reason that I have to pick a 2 here, right? So instead of a 2, I could have picked any function of y, right? So let's say I have like log of y squared, just to be consistent, I guess, with what I wrote above. Well, if I do that, then this means that instead of a 2 here, my function h has to be log of y squared, and I can just pick any function here, right? But maybe the log is confusing some people, but it's just like an arbitrary function. If you pick any function you want for the initial condition for u, you get a different solution, right? And so the key takeaway here, maybe that was kind of a long-winded example, but the key point is that for PDEs, initial conditions will always be functions, not numbers. Right, so you're not just, it's not enough to just, in general, just specify a particular number that the function is equal to at one point. You have to specify a whole function that it's equal to if you kind of isolate or fix one of the variables, right? And so for this example, we would actually have to have two initial conditions, right? We would need to fix some information about the derivative as well. Since this is just kind of like an informal introduction, I'm not going to continue on and be pedantic there, but we'll see examples like this shortly where we go through all the details. Okay, and so now that's kind of like the quote unquote like front matter to all of the lectures, kind of like all the, like, what is a PDE? What is the proper notation for writing PDEs? How do we talk about PDEs in terms of differential operators, etc. And so what we're going to turn to now is actually start looking at actual examples and trying to solve them. I think what I'll do is I'll since this is the first lecture and I don't want to overwhelm with information, I'll end things here. And so starting with the second lecture, we'll discuss a general method for solving what are called first order PDEs. Right, so we'll look at first order PDEs, which are of the form, right, I have some function, say a of xy times u of xy, sorry, the derivative of u, plus some other function, say b of xy times derivative with respect to y of u. And so we'll be looking at equations of this form, where a and b could just be arbitrary functions of x and y, and how, given that you, right, so assuming that these are fixed, the question we'll be answering is, well, what does the solution look like? And so we'll begin by looking at the simplified scenario where, let's say a and b are constant, right? And so then the equation takes the form, say a times ux plus b times uy is equal to 0. And so the question we'll be addressing is how to solve this equation, and then we'll look at the more complicated examples, and then move on to other topics. One thing to maybe point out, that's just to get you thinking before the next lecture, is to notice that, well, if I write this in vector notation, right, if I consider like the vector a comma b, and I consider the vector that has the first derivative, or the derivative with respect to x of u in the first component, and the derivative of u with respect to x in the second component, then this quantity on the left-hand side is just the dot product of these two vectors, and the equation says that this dot product has to equal 0. Well, what is the vector that has x derivative of u in the first component and y derivative of u in the second component? This has a special name. It's called the gradient of u. And so what this equation says is that a comma b, if I take the dot product with the gradient, this has to equal 0. Well, this should ring a bell if you think back to multivariable calculus. What is this? This is the directional derivative of u in the direction a comma b. And so what this equation says is that the function u if I take the derivative pointing in the direction a comma b in the plane, right? So maybe this is my plane and this is the point AB, and I move my input variable in this direction, then the function u can't change, right? Because the derivative is 0, meaning it doesn't change as you move along that direction. And so we're going to be able to use this geometric observation to solve the equation, right? So this is what we'll see next time. All right, thanks.